Welcome to Eureka Math. I'm Mr. Shankel. I'm going to be helping you today with Module 4, Lesson 24. Let's get started. All right, in the exercises today, we've got Derek, who scored 30 points in the basketball game he played, and not once did he go to the free throw line. That means that Derek scored 2-point shots and 3-point shots. List as many combinations of 2 and 3-pointers as you can that would total 30 points. All right, well, let's start out with what if he made no 2-pointers? What if he had 0 2-pointers? That means he would have to have made 10 3-pointers. 10 times 3 is 30. So that's a possibility. Let's see. What if he made 2 2-pointers? Well, 2 2-pointers, that's worth 4 points. So I would need 26 points, and I can't get 26, so 2 doesn't work. What if we made 3 2-pointers? That's 6 points. That would leave 24 points left to make, and 8 times 3 is 24, so that could be 8 3-pointers, 3 2-pointers. Let's try 6. If we make 6 2-pointers, that's 12 points. That would leave 18 points left to make on 3-pointers, and 18 divided by 3 is 6. Okay, so 6 3-pointers and 6 2-pointers, that would work. What about 9? 9 times 2 is 18. Take that away from 30, that leaves 12. 12 divided by 3 is 4, so that's 4 3-pointers. That would work. Let's see, we could make 12 2-pointers. That's 24. That leaves 6, and that's a possible 2 3-pointers. That's another possibility. And then the last possibility would be 15 2-point shots and 0 3-point shots. So that's all the ways that we can make that happen. And then we have to write an equation to describe the data. Well, I could use any one of these to help me to describe the data. So I'm going to say this. What if I made X number of 2-pointers and Y number of 3-pointers? Well, I could say that every 2-pointer is worth 2 times X, and then add that to every 3-pointer is worth 3 times Y, and that has to be equal to a total of 30 points. So 2X plus 3Y equals 30 is my equation. All right, so now let's continue. And Derek then says that the number of 2-point shots that he made is 5 more than the number of 3-point shots that he made. And we have to come up with some combinations. Well, let's say that he made 0 3-point shots. He said that the number of 2-point shots was 5 more than that, so that would be a 5. So he could make 0 3-pointers and 5 2-pointers. He could make 1 3-point shot and 6 2-pointers. He could make 2 3-pointers, and 5 more than that would be 7. He could make 3 3-pointers, 5 more than that would be 8. Could make 4 and 5 more would be 9. He could make 5 and 5 more would be 10. So those are some possibilities. And then we have to write an equation to represent the data. Well, the equation would be the number of 2-pointers, X, is equal to the number of 3-pointers plus 5. Right? Every time that's true, the X value is 5 bigger than the Y value. So X is equal to Y plus 5. So that's an equation that would fit. And then it wants to know which pair of numbers from the table would show Derek's actual score of 30 points. Well, I'd have to figure that out. I'd have to say, well, if he makes 0 3-pointers and 5 2-pointers, that's worth a total of 10 points. So that's definitely not it. This is too low. And if I went to the bottom here and checked that one, 5 times 3 is 15. 5 3-pointers is worth 15, and 10 2-pointers is worth 20. That's a total of 35. That's too much. So it's somewhere in between there, and I just have to try another one. So let's try 4 times 3, that's 12, and 9 times 2, that's 18. Well, 18 plus 12 is 30, so there it is. So that's it. The pair of numbers would be when x is 9 and y is 4. Okay, well, we have 2 equations. We have this one that we just wrote for this situation. We have x is equal to y plus 5. That's the first equation. And then we had this one from our last screen, 2x plus 3y equals 30. 2x plus 3y equals 30. And those are simultaneous equations. They have to work at the same time. They're also called systems of equations, but simultaneous equations, we have to add up 2-pointers and 3-pointers so they equal 30 points, but we also have to consider that the number of 2-point baskets was 5 more than the number of 3-point baskets. So we have to consider that as well. And so that's what we're going to do today is talk about simultaneous equations, and this is how we're going to write them. We're going to make them look just like that. We're going to use that bracket, and we're going to say these are the simultaneous equations that we're considering at the same time. All right, let's try another one. Ephraim and Fernie are on a road trip. Each of them drives at a constant speed. Ephraim is a safe driver and travels 45 miles per hour for the entire trip. Fernie is not such a safe driver. He drives 70 miles per hour throughout the trip. Fernie and Ephraim left from the same location, but Ephraim left at 8 a.m. and Fernie left at 11 a.m. Assuming they take the same route, will Fernie ever catch up to Ephraim? If so, approximately when? So let's break this down. We're going to write the linear equation that represents Ephraim's constant speed. And so we're going to go back here and we're going to look up Ephraim. Ephraim is a safe driver, it says, and travels 45 miles per hour for the entire trip. Right? So that's it. 45 miles per hour. 45 miles in 1 hour. That's Ephraim. And we need to write an equation. Well, we just have to say that's equal to y over x. And then we use the means extremes to say 1 times y, that's y, equals 45 times x, that's 45x. So y is equal to 45x. That is our equation for Ephraim. Part B, write the linear equation that represents Fernie's constant speed. Well, Fernie's constant speed is given here. Fernie drives 70 miles per hour. Whoa, my iPad just dropped. He drives 70 miles per hour throughout the entire trip. So I'm going to say 70 miles in 1 hour, and that's equal to y over x. And then I'm just going to use the means extremes. 1 times y is equal to 70 times x, 70x. And that's the equation for Fernie. Okay, write the system of linear equations that represents the situation. Well, we just talked about it in our last screen. The system is going to look like this. We're going to use this bracket. We're just going to write them both. Y equals 45x and y equals 70x. There's our two equations, simultaneous or system of linear equations. So we're really close here. We just haven't considered one part, and that is that Ephraim left at 8 a.m. and Fernie left at 11 a.m. That means that Ephraim has been driving for 3 additional hours. So I have to account for that. I have to say that he drives at 45 miles per hour. So I'm going to change this into y equals 45 times x plus 3. That shows that he is driving an additional 3 hours. So if x is the same, that's time, the same time for Efren and Fernie, we can't leave it at just x. We have to say that that Efren drives an additional 3 hours. So it's 45x plus 3. And then if I use the distributive property, 45 times x is 45x, but 45 times 3 is 135. So I'm going to change this equation into 45x plus 135. Okay, and there is our system of equations. All right, so I brought our system of equations, our simultaneous equations, over from our last screen, and now we need to graph these two lines. So let's go about doing that. Let's start with y equals 45x plus 135. The plus 135 is the y-intercept, so I'm going to mark that. That's about right there. And then I'm going to go up 45 and right 1. So 35 and 45 is 180. That's going to put us about there, and then right 1. So that's about where it's going to be. And that is our first line. So we can graph this through both of those points. It's going to look something like that. And that's the graph for y equals 45x plus 35. And then we'll also plot y equals 70x. Well, there is no y-intercept, so I'm going to start at the point 0, 0. And then I'm going to go up 70 and right 1. Up 70 and right 1 is going to be about right there. And then I can draw that line through those points. So this line is going to look something like this. Okay, and there's our two lines. The question E is, will Fernie, Fernie is the second one down here, the purple line, will Fernie ever catch up to Efren? Well, she does eventually, and where she catches him is right here, right there, right where they intersect. So that's after about 6 hours. After about 6 hours, Fernie will catch up. So we're going to say 6 hours later. According to the graph, it's an estimation, but pretty close to that. Or a total of, I don't know, around 450 miles. Okay, so at approximately what point do they intersect? Well, that is 6 hours. That's my x value. And about up here, which would be about 450 miles. And that's where they would intersect. All right, let's look at another one. Jessica and Carl run at constant speeds. Jessica can run 3 miles in 24 minutes. Carl can run 2 miles in 14 minutes. They decide to race each other. As soon as the race begins, Carl trips and takes 2 minutes to recover. Write the linear equation that represents Jessica's constant speed. Make sure to include in your equation the extra time Jessica was able to run. Okay, so let's start with Jessica. She runs 3 miles in 24 minutes. That's 3 over 24. And we're going to set that equal to y over x. And when I use means extremes, I get 24y is equal to 3x. And then I'm going to solve this by multiplying by reciprocal. And all of this is from our last unit. And that gives me y equals 3/24 x, which I can simplify to be 1/8. 3 goes into 3 once, 3 goes into 24 8 times. So y equals 1/8 x. Okay? And then we do have to say that she does travel an extra 2 minutes. So I have to account for that. So I have to say x, not just x, but x plus 2. X plus 2. So now I can distribute and get my actual equation for Jessica. And this is going to be y equals, well, 1/8 times x, that's 1/8 x, plus 1/8 times 2, that's 2/8, and 2/8 can be simplified to be 1/4. So there's the equation for Jessica. So I'm going to use that later. And then I need the equation for Carl. Well, Carl travels 2 miles in 14 minutes. So we'll use that, 2 miles in 14 minutes. We'll set that equal to y over x. And we get 14, oops, let me move that up. 14y is equal to 2x. And we're going to multiply by the reciprocal of 14. That's 1 over 14. Do that to both sides. And let's see, we get y equals 2/14, which I can simplify to be 1/7 x. And that is the equation. Y equals 1/7 x is the equation that represents Carl's race. All right, so now I need the system or simultaneous equations. So I'm going to use my bracket, and I'm just going to list them. Y equals 1/8 x plus 1/4, and y equals 1/7 x. All right, so we're going to use those on our next screen. So I'm going to copy those and bring them over. And let's see, I don't know if I can find a good spot for these, but I'll try to put them somewhere where they're not going to be in the way. Maybe over here. Okay, so there's our two equations, and we're going to graph those. So let's start with y equals 1/8 x plus 1/4. The y-intercept is at 1/4. That would be a 0.25, so somewhere in there. And then we're going to go up 1 and right 8. So I'm at 0.25. I'm going to go to 1.25, and then I'm going to go right 8. So 8 is here, 1.25. So my next line is going to be next point is going to be right about there. And then I can draw a line between those two. So there is the graph for our first runner, Jessica. And then we're going to do another one. And we're going to get this one for our second runner. So we've got no y-intercept, so that's the 0.00. So we're going to start down there on the origin. And then from there, we're going to go up 1 and right 7. Up 1 and right 7 is going to put us right there. And that new line is going to go right through those 2 points. So from the origin through, from the origin through that point, and there we go. It's going to look something like that. And now we can answer some questions. And the question is, when will Carl catch Jessica? So let's go back here. When will Carl catch Jessica? Well, it happens at the intersection, which it's out here a ways. You know, it's somewhere maybe out in here somewhere. Okay, so that's when it's going to happen, and it could be a number of minutes out here that we could look at. It might be, let's see, 16, maybe 17, 18 minutes or so. Or if I go to the number of miles, I could see that it's around 2.5 miles, maybe somewhere in there. So answering our question, if Jessica and Carl race for 3 miles, who would win? Well, let's go back. 3 miles would be up above this, and at that point, our second runner would be the winner, right? Our second runner is Carl. So Carl would catch up at about the 2.5 mile mark, and then pass Jessica, and he would win. If it was a 3 mile race, it would definitely be Carl. So This is Carl down here, and this one is Jessica. And that would be our answer for part I. Carl would win. Carl would pass at about the 2.5 mile mark and go away. So at approximately what point would Jessica and Carl be tied? We thought that was going to be at about the 2.5 mile mark. Okay? So we're going to be solving these systems of equations. Right now we're just kind of looking at what they look like on the graph, and that's your lesson for today. I hope that helps. I'll see you again next time.